Hey guys, it's Miss Johnson here, and I am here to bring you your 9-1 notes. It's our last unit. We're nearing the end, and today we're going to be talking about exponential functions. Up at the top of your notes page, it says Sam is working in a biology class with a petri dish of bacteria. He estimates that he has a colony of about 25 bacteria. Assuming the entire population of bacteria doubles every hour, find out how much bacteria Sam will have after 5 hours. So with a question like this, it's pretty easy to make a list. Our 0 hour, or in other words, our starting point, is at 25 bacteria. Now we know that the population is going to double, so what we could assume is that after the first hour, he'd be at 50 bacteria. After the second hour, it would double again and go to 100 bacteria. Third hour, 200. Fourth hour, 400. And fifth hour, he'd be at 800 bacteria. So that's about how much he would have after 5 hours here. Now, it's pretty reasonable to make a list when we're only looking at 5 hours and when we're talking about doubling. But when you start looking at values that are not whole numbers, like multiplying by 2, maybe you're multiplying by 1.5 or a different sort of decimal, or if you're trying to do it beyond 5 hours, maybe you want the 10th hour or the 20th hour or the 100th hour, it's not really reasonable to make a list like that. So what we do is rewrite an exponential function instead. An exponential function for this equation would be y is equal to 25, because that's our starting value, times 2, because that's our growth rate, to the x power, x being our portion of time. So in this case, if I wanted the 5th hour, I'd have y is equal to 25 times 2 to the 5th power. And if you plugged that into your calculator, you would indeed find that 25 times 2 to the 5th power is 800 bacteria. So let's just recap some functions that we've looked at so far this year. Functions that we've worked with so far this year. We've definitely worked with linear. We're good with those. We know about quadratic. We know about other polynomial functions we looked at here. Those are the ones that are the x to the third, or the x to the fourth, or x to the fifth. We definitely looked at square roots, where we had that starting point and then it only continued in one direction. This was all chapter 7, by the way. This was all chapter 6. This was chapter 5. And that was everything before. Rational functions we just looked at back in chapter 8. Those were functions that we had the vertical asymptotes and we had the wholes. So these are the functions that we've definitely looked at so far. Now we're going to look at exponentials. So here's the properties of exponentials and the standard form. Now on your notes sheet, this is written pretty small, so you might want to circle it or highlight it if you've got a highlighter. That standard form of an exponential function is important to know. Y is equal to a times b to the x power. And here's our properties of these exponentials. The function is continuous, meaning it goes on, and one-to-one, meaning there's only one y value for each one x value. That makes it a function. The domain is the set of all reals. We're always going to have all reals here, or we can plug in any x value for that exponent. The x-axis is going to be an asymptote of the graph, and we talked about asymptotes a little bit in chapter 8. Asymptote means that it approaches but never crosses. So it's important to know that your graph is never going to touch that x-axis. The range of the function is all positive if a is greater than 0, and all negative if a is less than 0. So it's either all above the graph or all below the graph, depending on that a value. The graph always contains the point 0a, meaning this a is your y-intercept. Okay, a is always going to be the y-intercept of the graph. That's an important thing to know. That'll help you graph it for sure. And y equaling a times b to the x power and y equaling a times 1 over b to the x power are reflections across the x-axis of each other. And you can see that right here. This graph going up like that, 1/2 to the x coming down like that. They're reflections across the x-axis, 2 and 1/2. So let's just try graphing a couple of these things. In number 1, I want to sketch a graph of y is equal to 3 times 2 to the x. Now we're going to do the same things that we have always done in the past. I'm going to take that equation and I'm going to plug it into my graphing calculator. I set up a value here, or a table here for you. So why don't you go ahead and plug that into your graphing calculator and see if you can figure out what values are supposed to go in that table. All right, so here are the values that I found for my table. The other thing that it asks me to do is to state the domain and the range. The domain, like it said, is going to be all real numbers. That was part of our properties that we just looked at of those exponential functions. The range, we need to look at the a value, which in this case, the a value is 3. Since the a value is greater than 0, my range is going to be the set of all positive reals. And now let's go ahead and graph that function. So I would put my points on the graph. Negative 3.375. Negative 2 is 0.75. Negative 1 is about 1.5. 0, 1, 2, 3. There's that y-intercept that we talked about. 1 is 6. There's 4, 5, and 6. And 2 would be 12. 7, 8, 9, 10, 11, 12. I'd be up there. I know my graph is going to curve up. Remember that that x-axis is an asymptote, so it never actually touches the axis. It just approaches it, and then it continues on in either direction. Let's go ahead and try number 2. In number 2, I want to sketch a graph of y is equal to 2 times a half to the x power and state the domain and range. So again, go ahead and plug that equation. Remember to put parentheses around that 1/2. Plug that into your graphing calculator and see what it looks like. Okay, so this is the table that I came up with. Now you can see that our values are decreasing there. The domain, again, is going to be all real numbers, because that's just a property of the exponential function. The range, again, my a value is still greater than 0, so even though my values are decreasing, they're all still positives. These are all positive reals. Even though they're going down, they're not negative. And then let's go ahead and put that on the coordinate plane. So at negative 3, I'd be up at 16, negative 1, negative 2, negative 3. That's way the heck up here somewhere. It's going to be way up high. Negative 2 would be 8. So see if I can get there. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I've got space. Negative 1, 4. 1, 2, 3, 4. 0, 2. There's that y-intercept we talked about. The a value is always our y-intercept. 1 and 1 and 2.5. So I know my graph is coming up from way up there somewhere, and I'm going to come down, and I'm going to graph, and it curves, and again, that x-axis is an asymptote, so it never touches the x-axis. It's important that you don't touch the x-axis. It's not going to cross it. It's just going to come really close to it. All right, so we've seen a picture of what exponential growth looks like and what exponential decay looks like. Now let's talk about what those functions might do for us. For exponential growth, I want to see, I know I'm going to have an a value that is greater than 0. I also know that I'm going to have a b value that's greater than 1. If I'm growing, that means my b value has to be greater than 1, or what would be 100%. If I'm growing, I'm going up from 100%. I'm starting with 100% and going up. If I'm looking at exponential decay, that means that I still have an a value that's greater than 0, because my graph hasn't flipped upside down to the bottom of the coordinate plane, or in other words, the negative values. But now my b value is between 0 and 1. It has to be greater than 0. It can't, actually, I should take that equal sign back off. It has to be greater than 0. It can't equal 0. If it's 0, then the whole thing is 0. But it has to be less than 1. So it's some sort of percentage, and that just goes back to decaying. If it's exponential decay, it's going down, so you're at only a certain percentage of what you started with. So let's just look at these little examples we have down here. What will the value of this do? Car, definitely decay. Car is definitely a decaying function. Gold is typically a growth function. The value of gold is typically something that grows. Houses are typically growth as well. Now, in our most recent economy, houses went down for a little bit, but that's just a small blip on the radar if you think of things over a large period of time. Computers definitely decay. Computers are like cars. The second you walk out of the store, there's another new one in the store. So that value is definitely going to go down. Let's just look at number 2, determine whether each function represents exponential growth or decay. So the first thing that I need to check is to make sure that my a value is greater than 0, and yes, it is here. This a value, it's like a coefficient that we don't normally see. It's 1. So my a value is 1, which is greater than 0. My b value is 1/5. That's the thing that's being raised to the x power. Since the b value is between 0 and 1, it's got to be greater than 0 but less than 1. That means that this is going to be dk. Okay. In part B, if I look at my a value is equal to 7, which again is greater than 1, so I'm okay, or greater than 0, so I'm okay there. But now my b value is equal to 1.2. Again, b is that thing that's raised to the x power. 1.2 is greater than 1. Since 1.2 is greater than 1, we're looking at exponential growth here. Okay. All right, so that's going to end our video for today. We took a look at a majority of 9-1. We're going to pick it back up with our application questions tomorrow in class. Thanks for watching. Don't forget to go back to Schoology and take that quiz, and I'll see you tomorrow.